myself. Just wait for a few folks to take their seats. We're going to welcome back Michael Garrett, a kernel developer from Red Hat. Matthew Garrett. I had a housemate named Michael Garrett. That's my problem. He was actually a good guy, but he didn't know anything about Red Hat. But Matthew does, and he specializes in power management, mobile and firmware development. Now, even though this is the last session, we're still being streamed, so we're still going to leave his opinions on firmware quality kind of, printable. And since he doesn't have any printable opinions, apparently, I'll just have you welcome him.
Hi. All right. Well, as was mentioned, my name is Matthew Garrett. I work for Red Hat. I have opinions on firmware. So are any of you familiar with Clout? It's a service that mostly tries to sell you things subtly, but it nominally works out what people are influential about on Twitter. So I logged in last week, and it told me that apparently I'm influential on the topics of Linux, hardware, and alcoholism. Which came as a surprise to me, but I suppose it makes some degree of sense. Anyway, I'm not going to be talking about my personal problems today. I will instead be talking about UEFI. So what is UEFI? Now, in the old days, you had a BIOS in your PC. It was some x86 assembly code that, when executed, configures your hardware and has some sort of configuration menu, and eventually would just jump to the beginning of a disk and start executing code. So it's all very straightforward. So obviously now we have to replace it with something else because it's only been around for 30 years, and obviously that's far, far too long in technology for something not to be replaced with something else. UEFI is a complete replacement for this. What's interesting about this is that the core of UEFI, the majority of the functional components, are released under a BSD license. You can download them from SourceForge, you can look at the code, you can modify the code, you can build an image that runs under virtualization and running QEMU, so you're even able to run your UEFI code. It doesn't have much, the open code doesn't have much in the way of drivers, and it doesn't have the platform initialization code, but we'll get to that later. Then adds standardized support for a bunch of new hardware features, things that right now you can't easily do in BIOS, you can do in EFI, because it gives an experience in the firmware that's much closer to an operating system. You get a lot more flexibility, a lot more control. You're able to do things that weren't otherwise possible. And it is, of course, utterly, utterly infuriating. So this slide is just taken straight from the UEFI specification. It just describes how EFI starts up. So to begin with, we have this platform initialization code. And this code is platform specific. It's the code that has to do things like configure your memory controller so you're actually able to access RAM so that later things can use RAM, which is usually considered a fairly basic requirement for a general purpose computer. And it'll also make sure that all the components are powered up. So that, like I said, very low level. That will be platform specific. We won't get the source code to that in a typical case. On top of that, we then have the core UEFI interface that I was talking about earlier. And this sits there. It started once we've done the platform initialization, and then we're in standardized EFI code. And this code is going to be shared between the majority of devices. All UEFI implementations I've seen are based on the Intel core code. Nobody has written a new EFI from scratch, which is great. So that comes up, and then that loads EFI drivers, so that EFI can do things like interface with your keyboard and your mouse, but also your graphics hardware, your disk, your USB, your network card. There's probably a UEFI driver for the majority of hardware components in your system. The only thing that's really missing is sound, which is a shame, because otherwise we could, in fact, port a fully functional version of Quake to EFI. But instead, we'll just have to make do with NetHack or Emacs. So EFI applications, the EFI applications can use EFI services to do basically arbitrary things. It's protected mode C, you just write in C, you make EFI calls. There is even a port of the standard C library, so you can just write C directly at EFI and build it, and then you get a .EFI binary that you can run on your firmware, which is neat if you've ever decided that what's wrong with operating systems is that they're just too useful, and you'd prefer to run what is effectively in many ways a 32-bit version of DOS. You can now just do that from your firmware. You don't even need a hard drive. Wonderful. One of the EFI applications is typically a bootloader. So EFI has a bunch of boot variables. One way in which EFI is actually better than BIOS is that instead of the bootloader just being written into a specific location of the disk, you instead give EFI a path to the bootloader. And so long as EFI knows how to read that file system, the only one you're guaranteed there is FAT. But of course, you can give EFI, you can write a file system driver for EFI, load that from a FAT partition, and then boot the kernel off an arbitrary file system. So you point it at the bootloader, and then EFI executes your bootloader. And your bootloader is just a normal EFI application. And one of the things the bootloader does is obviously call into the firmware to read your operating system off disk. And once you have your operating system in memory, once you've finished all of this initialization work, you exit the boot services, and at that point, all the EFI, well, the majority of the EFI code is then discarded from memory and is usable by the operating system. So we then jump into the operating system, and from that point on, you're running Linux instead of EFI. It's all well and good. That's fairly straightforward. There's two kinds of services provided by UEFI. There's boot services, which are a rich set of interfaces with the hardware. They're all these graphics, USB network drivers, and so on. They let you do a huge range of things. And then there's the runtime services, which are a much more limited operating system and firmware handshaking interaction layer. Boot services do things like permit memory allocation. They let you set up timers. They load images off disk, that kind of thing. It's very easy to use the boot services. EFI is one of these things where somebody decided that the best way to solve the problem of namespacing was to use GUIDs, because that way you have a flat namespace with no collisions, and nobody can ever remember anything because it's a long bunch of hex for you to be able to do anything, but could be worse. You make an open protocol call with a specific GUID, and then that hands you back a table of function pointers, and then you just call those function pointers, and that performs the EFI call, and then something happens. So it's all pretty straightforward and easy. So here's an example of an EFI protocol definition. So we have this wonderful, catchy GUID there. As you can see, I'll admit, I'm sorry to disappoint those of you who think that I'm particularly good at this. I cut and paste that. I didn't remember it and then write it down. And then we have this struct. And the struct is just a bunch of typedefs of pointers to various functions. So if you want to know the graphics mode that you're in, you call open protocol with that GUID, and then you get back one of these tables. And then you call query mode with the appropriate arguments, and you get back a structure that defines your current mode. And if you want to change the graphics mode to another mode, then you just repopulate that mode with the modes that you want and call set mode, and then the firmware changes the resolution for you. There's also blissing support, so you can render to an off-screen buffer and then bliss it into the graphics hardware if you want to write a high-performance graphical application for EFI, for instance, and then just a point to the current mode again. So it's pretty easy. Writing applications that interact with EFI is actually not a particularly awful, traumatic event. Yeah. Anyway, there's then the point where we cross between the firmware and the operating system. The boot services are, like I said, they're primarily things for memory allocation and drivers interacting directly with the hardware. Once you've got your operating system, you're probably going to be using native driver calls. So at that point, there's no reason to continue using the boot services. So otherwise, it's just going to be sitting there in RAM and taking up resources that you don't need, completely pointless, bloaty. So we have this call we make, exit boot services, and you call exit boot services, and that tells the firmware that there will be no more access to, the operating system will make no further attempts to access boot services. And after that, that code's discarded, we get all the RAM back, and we only have to carry the extra resource hit of the runtime services code. The kernel then has to call this set virtual address map function, and the reason for that is that when we make EFI calls, in runtime services are pretty similar to the boot time services. There's a table with a bunch of function pointers, and we call those directly. So there's no system management trap like there tended to be on BIOS. We still use the operating system's page tables. So the firmware needs to know what the virtual to physical memory addressing is, because otherwise you have a bunch of pointers and they're pointers to physical addresses. If you try to call those from within the kernel, then it'll explode because we need to be using virtual addresses. So the kernel tells the firmware what its address map looks like, and then from that point on, we can make these calls using the operating system's page tables. That's nice because it means we don't need to keep loading new page tables every time we go into EFI, which would be kind of a performance hit. And also we need to make sure that the runtime services code is executable because, like I said, we're in the same context as the kernel. Our page table is set up the same way. If we don't flag code as executable, then if we attempt to execute it, the CPU will give us a fault and the kernel will fall over, which is embarrassing. The runtime services give us various bits and pieces. There's a non-volatile variable store. So as I said earlier about the, you pass the path of the bootloader to the firmware, that kind of thing is stored in variables with a specific name, boot 0080 or something like that. And you can actually have multiple different bootloaders provided, and then the firmware can give you a menu that lets you choose between them. But we can also, sometimes we get system information out of there. There's various variables that's been populated by the manufacturer that potentially tell you something about the machine. But we can also put crash dumps there. The problem with traditional BIOS systems is that there's no non-volatile storage other than the CMOS, and that contains BIOS settings. And if we attempt to write anything into there, then the BIOS gets really unhappy, and also there's only 256 bytes. And unfortunately, Linux backtraces don't tend to be very concise. And you've seen them scrolling off the top of your screen when you're running in a high-resolution mode, and you've got a backtrace that's about 20 entries long. That's not going to fit so well in 256 bytes, even if we could use all of them. EFI, thankfully, gives us much more space. We typically have several kilobytes to play with. Average variable size is up to about 8K. So we can dump, if we crash, then the last thing we do before just halting the system is we can drop the backtrace into an EFI variable. And that's actually now done already on 3.2, maybe 3.1, 3.2 or higher. If you build in EFI variable support and you have the pstore interface enabled, then whenever you crash, stuff will be written to EFI variables, and then you can just mount the pstore file system somewhere and read your backtrace back out. It's great. I've already managed to fix a bug by taking advantage of this, which is nice because I wrote it in the first place, and so it's nice to feel that occasionally something I've written is useful. There's timed alarm configuration. This means the operating system doesn't have to know what your clock hardware looks like, despite the fact that traditionally all PC clocks have been identical. You no longer have to have identical clocks. You can now have different clocks. One downside of this is that the EFI specification does require that the time in the clock be stored in local time, not in UTC. But it also has a time zone field, and it also has a flag that indicates whether or not it's been updated for daylight savings. So you can implement it in such a way that operating systems don't fight over it. It's still kind of a pain. ACPI 5 behaves exactly the same way here. Again, kind of annoying. And then there's a call to reset or power off the system. There's a way to pass updates to the firmware. And that's quite nice, actually. You take a BIOS update, and you load it into memory, and then you make this call. And the firmware copies that into some reserved memory and sets a flag, and then you do a warm reboot, and the firmware sees that this flag is set, pulls the update out of RAM, and then reflashes it. So we no longer need to boot Windows just to update the BIOS. That's actually a nice feature to have. And finally, there's an interface to get a monotonic count that's used in some of the legacy ways of updating authenticated variables. You probably never need to care about that. I certainly don't. Now, EFI actually goes a little bit further than firmware specification in that it also includes the specification for the GPT, the GUID partition table. The traditional PC partition map, or the MBR partition map, only allows you to have 4 partitions unless you use extended partition tables, which then make things more difficult. It only allows you to deal with disks of up to 2.2 terabytes if you're using 512 byte sectors, which you almost certainly are. And it doesn't tell you that much about the partitions themselves. So you have a single byte field that allows you to specify the partition type. And only 256 values available. Some of them have got reused. I think there's overlap between Solaris swap partitions and OS2 system partitions or something. So if you look at a partition editor, you don't know whether it's an OS2 partition or a Solaris swap partition. You do know that it's completely pointless and irrelevant to you, but you don't know which flavor of pointless and irrelevant it is. And it also lets you provide a Unicode string that allows you to freeform describe the partitions. So you can actually give your partitions names now as well as your file systems, which is great because then your partition editor can show you that and you are much less likely to delete the wrong partition. It does mean that we then have the interesting issue that you could put Unicode control characters into your partition name, and then maybe your partition editor would get very, very confused and format everything badly, and maybe switch to right to left text. I don't think this is a particularly practical attack, but it's an opportunity for people to make mistakes. So GPT, it lets you have as many partitions as you want. It lets you have partitions of basically arbitrary size. You can have disks that are 2 to the some large number bytes long, which is probably, I don't know whether it quite reaches more atoms than there are in the universe, but it's probably an approximation of that kind of thing. Now, this all sounds pretty good. I've just given you a bunch of reasons why UEFI makes life better. And obviously, if that's what I was here to do, then this presentation would be, well, over at this point and not especially interesting. There's quite a lot of, there are issues with EFI. As I mentioned, Tiano Core is the code name for the open, available, BSD licensed core of UEFI. And it's written primarily by Intel. It's used as the basis of the EFI development kit, and then the EFI development kit is in turn used as the basis for most system firmwares that are UEFI based. And it's incorporated pretty much unchanged. If you take a vendor firmware and you start disassembling code, you can normally map it pretty much precisely back to the UEFI code. And it's made up of files. What else would it be made up of? It's made up of rather a lot of files, containing quite a lot of code. And in fact, it's approximately 10% of the size of the Linux kernel. Now remember, as I said, the Tiano Core stuff doesn't really include much in the way of drivers. It's got a couple of USB drivers and a basic IDE implementation, but otherwise, this is effectively the kernel core. So if we compare fairly, if we exclude all the drivers from Linux, we actually end up with EFI, the Tiano stuff, potentially being bigger. And if you take into account the platform initialization code, it's certainly larger than the Linux kernel. Now, files contain code. This is unfortunate. It would be great if files didn't contain code. If we could get rid of all the code, life would be much easier. Because code contains bugs. All of it. You think that your code contains no bugs, and then you find that there's a bug in your compiler that introduces a bug into your code when it builds your otherwise bug-free code. Code is just an embodiment of bugs. So UEFI contains files, files contain code, code contains bugs. Therefore, UEFI contains bugs. It's not particularly surprising. It's a large body of code. Now, obviously, the Linux kernel, despite being a large body of code, contains no bugs. But it's an exception, and we can't really expect everybody in the world to meet our high standards. You can tell that Linux contains no bugs because when Bugzilla kernel log went down, there were no bugs. It's all absolutely fine. Has anyone here ever seen a Linux kernel bug? Are you really that scared of me? Okay. So there's quite a lot of bugs. I've found many of them myself. It's been wonderfully entertaining. One might almost think that this code was almost completely untested. So yeah. Exit boot services, I mentioned. Once you've called exit boot services, the specification says that the boot services code can now be reclaimed by the operating system, and the firmware will no longer assume its existence. Set virtual address map has to be called after exit boot services. I'm not sure why I've written exit boot serves. Sorry about that. Exit boot services. So set virtual address map has to be called after exit boot services. If you try to call it before exit boot services, it returns an error code that translates as this function must be called after exit boot services. So we're really very clear on the fact that it has to be called after exit boot services. So given that it has to be called after after exit boot services, there should be no way in which set virtual address map calls any code in boot services, right? And this is around the time that I start crying gently and wishing that maybe I had actually stayed working with fruit flies. What we instead get in some cases is set virtual address map calling into some boot services code. And it's very easy to see that it's doing this because the kernel attempts to execute that code. And we were lucky. In the systems I was testing this on happened to have, there was no kernel code loaded there. It would have been valid for the kernel to have put bits of itself there, but it hadn't. So as a result, this memory was unused, and therefore it had not been flagged as executable. If it had been flagged as executable, then we would have executed it, and who knows what would have happened. But it was okay, we just took a fault and the kernel crashed. And then you look at the pointer of the code it was trying to execute, and you look at the memory map and you see that it says, oh, this is boot services code. Well, that's interesting. So now we have to preserve the boot services code until after we've called set virtual address map. This, it turns out, complicates the kernel immensely. And we went through various iterations. We ended up with what is probably the ugliest code I've ever written in my life ever, and that includes before I understood C. But wrote it anyway. And now we work around that bug. Intel actually traced this down to a bug in the EDK. Apparently it's been fixed in the EDK2, so recent systems shouldn't have it. But basically almost all systems produced in 2010, 2011 with EFI have this bug. And they're not actually going to go back and fix it in all the release system BIOSes, because that would be awkward and unpleasant and expensive, so we're stuck dealing with this bug forever. Because all computers never die. They sit there to generate bug reports. Moving on. Virtual memory is great. Your mapping between physical addresses and virtual addresses is no longer direct. It doesn't have to be the same mapping from any given physical bit to any given virtual address. And so obviously the firmware should be aware of that, given that the firmware is written by people who write software, and people who write software should understand how computers work. Turns out that there are cases where this is manifestly untrue. Some Apple laptops come with an EFI memory map that defines 4 regions that are flagged as required for runtime access, which means the operating system has to map those into the virtual address space so that the runtime services calls can take advantage of them. Now, they had contiguous physical addresses, so it was 4 blocks with identical attributes that covered one contiguous 2 megabyte block of physical address space, but split into 4. Linux mapped them to non-contiguous virtual regions. So if you have these contiguous virtual regions, then they could be mapped to this non-contiguous one. Now, say you have a pointer into the first block here. If the blocks are contiguous, then you can access the last block just by adding a constant offset. If the blocks are non-contiguous, doing that results in you pointing into the middle of nowhere. It turns out that in this case, what these blocks represented were the flash on the device. So when you called set variable, it needs to write to flash to write the new value. And it was taking an address into the first block and adding a constant offset in an attempt to write into a later block. And if you were lucky, then that Linux would have mapped it like this, and your kernel would oops. And this is one of those rare cases where when I say, if you're lucky, your kernel will oops, I really, really mean, if you're lucky, your kernel will oops. Because this mapping is not guaranteed. Different kernels might end up with different maps. If you add a piece of hardware, the memory map may end up differently. And you could instead, for instance, end up with a map that looked like this, which means when you attempt to write, you do actually succeed in writing somewhere in flash, just not where you thought you were writing. And in fact, when we were trying to set the boot variable that pointed to our bootloader so that when you reset, the system would boot Linux, we were instead actually writing that ASCII string into the middle of the boot firmware. And this is considered problematic, since the system then stops booting forever. And we can talk about this now because it's now been fixed in several versions of the Linux kernel, but there was a point where if you attempted to install Linux on various types of MacBook Pro, you would, if using EFI, reliably destroy them. I think most people were lucky enough to be able to get that covered under warranty service, but you know, it's always depressing when you realize that, yeah, back when you were a kid, you were potentially told, oh yeah, feel free experimenting with software, there's no way you can damage the computer. It's lovely how we just believe that children need to be shielded from the truth and therefore lie to them viciously. So that was unpleasant, that was unfortunate. That one resulted in, again, tears, crying, weeping, and gin. Now, many other bugs we found have also been in the variable code. There was one machine which was shipping with a shipping BIOS image, and it's not like this was pre-production hardware that we were testing. If you set a variable, that worked fine. If you attempted to delete the variable, it failed. Now that's fine. You install Linux, and you install the bootloader, and the bootloader string includes the GUID of the partition you've installed it into, so that it can be uniquely identified. So then, say later, you reinstall. Maybe you swap the hard drives out, or maybe just reformat and start from scratch. We then attempt to we recreate the partition, which now has a different GUID, and we attempt to rewrite the variable, and writing the variable fails, which is awkward. As not only does writing the variable fail, the existing contents of the variable now point at a partition that no longer exists. So you reboot, and your system doesn't boot. Which is interesting. It Also, interestingly, Linux and Windows by default use different boot variable names. So you could install Linux once, and you could install Windows once. But if you attempted to install either Linux or Windows for a second time, you couldn't, ever. And another one, you call the interface that gives you a list of variables, and it gives you the same variable twice, which is not really in the spirit of the spec, in that it's a blatant violation of the spec. Rebooting, straightforward, easy, wonderful thing. You should be able to reboot a system, no problem at all, ever. There's an EFI call to do this. You make that EFI call, and on most systems, it attempts to access physical addresses directly. This doesn't work because we still have the kernel's virtual physical page tables loaded, and so instead of rebooting, we oops. These are the bugs we found in the runtime code. Boot time services code, there's a lot more of that. And thankfully, as people working on the kernel, I wouldn't have to care about this, except for the fact that I also have to work on grub for EFI, which means I do need to care about it. So, the moral. Straightforward, easy moral. UEFI is poorly tested in the real world, UEFI contains a lot of code, and UEFI contains quite a lot of bugs. I wouldn't say that it is. I'm not saying that UEFI has more bugs than a typical piece of poorly tested software. Merely that EFI has approximately the same number of bugs as an average poorly tested piece of software. And that's plenty of bugs. Anyway, one thing you've probably heard rather a lot about in terms of EFI is secure boot. Has anyone here not heard about the UEFI secure boot issue? Okay, a few of you. Right, well, I'll give you a brief introduction. Secure boot is intended to be a mechanism for protecting systems against early pre-operating system attacks. Nowadays, even with Windows, security is reasonably good. Even if you exploit the kernel, it won't be too long until there's an update that'll fix that. And also, there will be an updated malware checker that will notice that your system is infected. The problem is that if you can execute your code before the operating system has started, that means that you can modify the operating system to lie to itself, which then means that the operating system will say, everything's fine. I can't see anything here, because you have a bit of code that is busy going, these are not the droids you're looking for. And this happens in the real world. There are now viruses for Windows that will write themselves into your boot block and will then, on the fly, modify the Windows bootloader, modify the Windows kernel, and then patch them so that any attempt to read the area of disk that contains the malware will fail. You'll get back what looks perfectly normal, but actually that's a lie. It contains evil. Secure boot aims to protect against this by only permitting trusted code to run before the operating system starts. And it does this by using encryption. There are a bunch of keys. There's PK, which is owned by the vendor. So when you buy hardware, the PK variable has been set by the platform vendor. PK is used to control updates to the KEK. Entries in the KEK are provided by operating system vendors and allow you to update DB, which is a whitelist, and also DBX, which is a blacklist. So if you have a KEK, then you can add signing keys to DB. When you attempt to execute an EFI binary or load an EFI driver, you grab the file and you look for a bit in the header which contains a signed cryptographic hash. So the hash has been signed with the private half of a key that's in DB. Using the public key out of DB, you decrypt this, and that gives you a hash. You then perform the same cryptographic hash of the object, and if the answer you get is the same, then you know that the file hasn't been modified since it was signed. And you assume that whoever signed it was actually competent to determine whether or not this file could be trusted, and so you execute it. If they don't match, you refuse to execute it. The operating system knows it's being booted securely, so you sign the bootloader. The bootloader will only be executed if it's appropriately signed. The bootloader will then launch the kernel if the kernel is appropriately signed, and then you go up from there. And then the operating system knows that it's being booted securely because when it calls get variable, there's a variable called secure boot that will be 1. And unfortunately, the firmware, you're calling into the firmware to get this value back, which means that if the firmware has in any way been compromised, if any untrusted code has been written before you, then it can tell you that you booted trusted code when actually you didn't. So if there's any opportunity for anything to interact with the firmware before the operating system starts, then you've lost. Which means that all code with hardware access must be trusted. The firmware code has to be trusted. The firmware must validate that it is correct. Normally it'll do that just by the fact that it's reading it out of flash, which means that it probably couldn't easily be modified by the user. So the only trick there is that firmware updates now have to be signed. You can't reflash your firmware with modified firmware unless it's signed by the platform vendor. All the bootloader code has to be signed because the bootloader is running in the firmware, and so obviously the bootloader could modify the firmware because while stored in flash, the firmware is running out of RAM. So it can modify the running copy of the firmware. And all your kernel code, because your kernel you could boot Linux, and then if the kernel code is untrusted, something you could do with Linux would be to set up a fake EFI environment. And then, you know how kexec lets you boot from Linux into Linux? It would be possible to jump from Linux into Windows. So you could use Linux as a malware bootloader. You could modify state, and then you could set the secure boot flag to 1, and then you could jump into Windows. And so the kernel code has to be trusted. All the kernel code has to be trusted, which means modules have to be trusted, which means modules have to be signed, which means, you know how right now you download out-of-tree drivers for, say, an NVIDIA card or whatever, and then you build those locally to match your kernel? You're not going to be able to do that anymore. Not if you use secure boot, because otherwise, if you could load an untrusted kernel module, you could then use Linux to Trojan Windows, even on secure boot systems. So we don't know who gets the keys. The signing keys are obviously the aspect that controls you here. There is no defined policy right now as to who gets the keys. Microsoft simply insists that vendors carry their key if they want to get a Windows 8 sticker. Microsoft have a little more of the market than us, so they have a little more influence over hardware vendors than we do. But we could probably imagine that the bigger Linux vendors, the Red Hats, the Canonicals of the world, could probably get signing keys and could probably get those introduced into the majority of systems. And that's all fine unless you're a Debian user, or a Gentoo user, or an Arch user, or any of these other Linuxes that I hear the young people are so interested in these days. And then there's a license issue. GPL v3 requires that any signing key be available so that users can generate their own replacement versions of binaries and sign them. And if we hand out the signing keys, then the first thing anybody would do would be to sign some malware and use that. And it means that out-of-tree driver vendors suddenly have real difficulty. Although, as a kernel developer, that one may actually be a benefit to me, given how awful many of them are. But it means things like VirtualBox. You won't be able to build the VirtualBox driver for your kernel, which means you can't run VirtualBox, which, again, sounds like a benefit to me, but apparently some people like it, so. Anyway, we have a lot of issues there, and the concern is that the Windows 8 logo guidelines, logo requirements, require that any system shipping with a Windows 8 logo sticker must be shipped in secure boot mode and must execute only secure binaries unless you go to the firmware and turn an option off. And going into the firmware, that involves you having to deal with the fact that, I said EFI lets you do graphics. People have decided that what the world's really been missing are graphical firmware configuration interfaces. So it could be that you'll go into the menu and then you'll choose an option marked security, and then there'll be secure boot, and you change that to no. Or it could be that there'll be a rotating 3D sphere, and you use the mouse to drag that around until the word security appears in giant letters on your face. and then you hold down Control-Alt-Meta 5, and then that disables secure boot. That would be valid per spec. It's very difficult to write install instructions when the instructions differ for basically every computer on the market. Your Linux install instructions then turn into a kind of book. So we have concerns, and we don't as yet have a full set of solutions. And we have about 6 months, maybe 9 months, until these machines are the ones in the stores. Still, sorry, I can't really be more positive there. Anyway, you've been a wonderful audience. You've been much better than the audience I had earlier in the week, because that audience forgot to turn their phones off. And I think we have 10 minutes or so for questions, if anybody would like to take advantage of the fact that I'm upright and still speaking English.
So do you actually need to prove somehow that you're a secure distribution before you can get a signing key? And if not, what's to stop you from just accidentally forgetting to require signed modules?
Okay, so prove to whom? Because right now, the only people with a key that's guaranteed to be in a system and with which you can then sign other keys is Microsoft. So I suspect that Microsoft are going to want to be fairly convinced. If a key is used to sign something that then allows Windows to be attacked, Microsoft can push out an update through Windows Update that adds that key to the blacklist. And then there's no way to remove entries from the blacklist. And then BIOS updates will probably also include this key in the blacklist. We don't know what the policy for blacklisting keys is going to be yet. Microsoft won't tell us. We have asked, and they've said that they don't know yet either, which is reassuring. It's always nice to know that a company that is pushing through a completely market-changing technology has thought through the consequences of it fully. Really glad. It leaves me in such a good mood.
It's a gin, right? Just wondering, is there anything in the UEFI spec for what happens when you're doing secure boot and you get to, say, the kernel or some part of it, and it decides, no, that bit isn't secure? Because, in the Xbox had the marvelous security of jump to 0, because that was obviously a bad thing to do. And
so the UEFI specification allows you to do various things there, including stopping, failing over to the next boot option, or prompting the user to the fact that they're attempting to boot unsigned code or inappropriately signed code, and do they really want to do this anyway? Microsoft forbids that. So when anybody says it's just a specification that Microsoft's following, it's a specification that Microsoft is insisting you follow parts of and explicitly saying that you can't follow another part of it. So what will happen is that the system will either attempt to boot. If there are multiple boot sources available, it'll fall back to the next boot service. If not, it will just stop, in the same way as if there were no boot entries available. And that, right now, that would probably just result in there being a blinking cursor on the screen and nothing else. In terms of how it will end up being implemented for certain, I can't say. As to whether you'll be able to use that to exploit anything, your guess is as good as mine at this point.
By the way, all of our audience members thus far have been great, but for those who haven't spoken yet, if you can speak over the microphone like I'm doing now, it makes life for our AV people a lot easier.
So my impression from this is that all things that are traditional PCs are going to start looking like iDevices, and we'll have to, root them somehow.
Right. And in some ways, I would love the PC market to be more like the Apple market, because I really like Apple hardware. I just dislike Apple firmware. And Apple software, but yeah. It is definitely the case. Well, Microsoft require that any systems sold with the Windows 8 logo that are x86 allow you to disable secure boot or to add your own keys through some sort of interface. they haven't said what that interface has to look like. So again, it's difficult to document. It's something that you can only do by sitting directly in front of the computer, going into the firmware option and changing things. So it's not something that's going to work for automated installations. They have, however, said that for ARM devices with the Windows 8 logo, secure boot must be enabled, and it must not be possible to disable it, and it must not be possible to do custom key installation. So any Windows ARM devices, I mean Windows 8 rather than Windows Phone, any ARM devices running Windows 8 will be locked, and you will have to find some exploit in order to boot your own code.
But that's okay, the software has bugs.
The suggestion that there are bugs in EFI is one I could neither confirm nor deny. Anyway.
Is it part of the spec for the operating system to be able to update and modify the keys that are stored, or is that something that would be exclusively within the EFI interface?
The spec permits keys to be added to the whitelist or to the blacklist or updated, yeah, as long as you have a key that's in the KEK. You need a key in DB to boot, but you need a key that is in the KEK database in order to add keys to the whitelist or the blacklist. So the spec permits it, but it means that you have to have an appropriate key in your firmware.
This will be the second most unimportant question you've heard this week. You said that Intel are the only ones that have written a UEFI implementation. Apple have UEFI in their machines. Did Intel write the code on the Macs?
The majority of the EFI code on the Macs is derived from the Intel code base, yes. The Intel code base was available before Apple started doing this, and I suspect that Intel, given that the move to Intel for Macs was done working quite closely with Intel, I'd be amazed if Apple had decided to write their own EFI code. It's certainly the case that some of the EFI bugs I've hit on Apple are definitely ones from the Intel code, because the same bug appears on hardware made by companies who are very much not Apple.
Do you know that the Windows 8 logo guidelines are completely fixed, or is it possible that some antitrust lawsuit will change that?
The guidelines are currently, the guidelines have already changed over the past 6 months. They are now much more liberal in this respect than they were in September, October, which is when we first started complaining about secure boot. And so that shows that Microsoft has paid some attention to the outcry. I would suspect at this point that Microsoft have sound legal representation, and their lawyers have probably advised them quite closely on whether or not a given act is one that carries a significant risk legally. Beyond that, I'm not a lawyer, I can't give legal advice. I would be surprised if this ends up as an antitrust case, certainly in America. Maybe Europe, where the market's slightly different and regulators have slightly stronger opinions about rampant unchecked capitalism. But we can't guarantee it, we can't rely on it, and it would certainly end up coming far too late. This kind of thing would take years to do through the courts, and like I said, we've got, by the end of the year, most hardware shipping is going to be UEFI based and implementing secure boot. Except Mac hardware. We don't know what Apple are going to be doing. Apple could implement it themselves as well. We really just don't know at this point.
So I've got time for a couple more questions. There was a hand up here, and I'd particularly like to hear from anybody who hasn't asked a question yet at the con. But I think somebody here was first.
So how about the instance that I buy some new hardware but I want to run an older operating system that doesn't have UEFI support?
So you could disable secure boot. If you buy components, then it's possible that they won't default to EFI. If you've bought a machine from scratch, like I said, Microsoft require that you be able to disable secure boot. And then if secure boot's disabled, the UEFI will also allow you to fall back to BIOS compatibility, which will execute pre-UEFI operating systems. So the risk is not really to people who know how to interact with computers. Enthusiasts are still going to be able to run pretty much whatever they want on x86 for now. The risk is that Linux is going to become more difficult to install for the naive user, and that's not the direction we've been heading in. So that's the problematic aspect. It's difficult rather than impossible.
Anybody else? Like I said, particularly anybody who hasn't spoken yet this con, but there you go.
Just for the benefit of those who didn't hear you the other day, could I ask you to repeat your thoughts about secure boot and DRM and how it is not a DRM
right.
method?
Yeah, that's important. Like I said, it's very, very easy for you to tell the system that it's booted, tell the operating system that it's booted securely, even when it hasn't. There's no way for the operating system to verify that the answer it's got back is correct. That means that it's not DRM in any reasonable sense. Any attempt to believe that you were booted securely is doomed to fail. So it is really, really important that if anybody argues that Secure Boot's a DRM system, you convince them that it's not a DRM system. Because otherwise, if people believe that Secure Boot is DRM, then there's a real risk that any attempt to do anything interesting with Secure Boot will run foul of the DMCA or similar laws that restrict playing with DRM mechanisms. So yeah, if you see anybody saying that Secure Boot is DRM, tell them it's not, and if possible, explain why. But it's really, really not DRM. Vitally important that nobody be convinced to think that it's DRM.
Sorry, mate, there's no more time for questions. Just wanted to thank Matthew for his encore performance at this con. And thank you for all of your contributions as well. We have our lightning talks coming up after lunch. Hope you enjoy those. Oh, after afternoon tea. Well, no wonder I feel so head spinning. I haven't had lunch yet.